Log on, tune in, find out. Another good idea from Cambridge.
Talk is by Chris Farmer from Occam. There you go.
Oh yes, very much.
Beat the unbelievers with a stick, please.
This is not going to be so. Thank you to the organisers for giving me a chance to speak to you about my work. It's going to be a bit of an overview and also indicate where I'm trying to head at the moment. So this is about inverse problems. I do think that data assimilation and parameter estimation are exactly the same.
You can turn it on.
Oh,
On top, the small one. Yeah.
is that on now? Right. So data assimilation and parameter estimation are the same thing as inverse problems. There is a problem of terminology, but I take the view that there's no point arguing about words as long as you use them in a consistent way. So what I'm going to do is I'm going to talk about what I regard as the canonical inverse problem, that of interpolation. And I'll do this in a Bayesian way. I may as well come straight out of the closet and use the big B word immediately. So I will relate this to Tikhonov regularization and traditional interpolation in Sobolev spaces. Then I'm going to talk about a dynamical system, and I will talk about how we will solve that dynamical system using a sequential form of what's sometimes called history matching, and it relates to the work that Peter Yan talked about earlier. And I will outline an algorithm that I'm trying to get to work, and then a bit of a discussion, and I'll say something about the key literature. Let's get going. So this is what's known as scattered data interpolation. So really simple problem, but gives rise to large textbooks. I mean, it's a subject in its own right known as geostatistics or spatial statistics. So the problem is this. So let's do it in 2 dimensions. We can do it in any number of dimensions, of course. But we have some points here, and let's assume for the sake of argument that we know where the points are without error. There's a substantially difficult generalization to the case where you don't know where the measurements were actually made. Now, at each point, we'll assume that we have a function value that's been estimated. Now, when you're a numerical analyst, you live in a paradise, or some of us would regard as a fantasy land, where the function values are actually known at these points, at least to a very, very small error. People worry about many significant figures. But of course, outside in the practical world, these functions may only be known very, very imperfectly, with very, very large errors indeed. So the problem is to reconstruct the function given the values. Now, we all know how to do this the other way around, given a function, estimate the values, but how do we do it the other way around? Now, the obvious way to do this, if you're a numerical analyst, is to do, for example, radial basis function expansions using, say, a Gaussian radial basis. And that works very nicely in the sense that it gives you an answer. Whether the answer is defensible or not is another matter. And when I talk about a method being principled, all I mean is it's consistent with the principles of Bayesian statistics. And if I was to summarize those in one sentence, I would say being Bayesian and being principled is the same thing as being logically consistent when you argue in a deterministic way. So it's a very, very weak constraint on your reasoning. It just says that you need to balance probabilities. So here we are, how are we going to do our interpolation? So I'm going to introduce, you might think I was a numerical analyst doing this, except I'm giving away my physics background by calling it the energy rather than the norm. So let's have a general functional, which is a sum of the integral of the square of the function, the gradient, and the Laplacian squared. And these are positive coefficients here. A and C are positive, B could be negative, and there's a little inequality that says what they must be for the whole quadratic form to be positive definite. Now, using Gauss theorem, I can rearrange this, and I can get a quadratic form here, assuming the right sort of boundary conditions. I don't want to go into detail in the limited time I have. And then I get this operator L here, which is just a constant minus B del squared plus C del squared, which is the biharmonic operator. Now, what you can see here for the Tikhonov people, this is a weighted sum of 0, first and second order Tikhonov regularization terms. And I'm going to use this as a norm, but I'm going to interpret it in a probabilistic way. So if I take the negative exponential of this quadratic form, evaluated around what we'll call a center, phi r, for a function phi, then this is the probability density on the function space that phi belongs to. Now, Henning said that he worries about these constants, because I have a physics background, and physicists will remark that this happens to be an infinite constant, but it's an irrelevant infinite constant because it cancels out. But if you want to do it rigorously, you have to work really hard. And there's a whole group of mathematicians in the UK, represented by Andrew Stewart's group up in Warwick, who go about doing this in a... what's happened there? Ah, good. It's just my screensaver. Right. Okay. Right, so I write down this probability density. If I discretize this on a grid using any method, then it becomes a quadratic form, and it's just a multivariate Gaussian correlated random vector for a vector phi in some n-dimensional space. Now, there's a theorem, I don't have time to prove it, but the correlation, so if I integrate over the function, so this is a function space infinite dimensional integral, if I integrate over the space, the mean of this density is phi r, as I've called it the center. And the correlation function associated with this is actually the Green's function of this operator. This is why theoretical physicists refer to correlation functions very often as Green's functions or even Greenians. And it's very easy to prove. So if you discretize it, all you see here is this G here is the inverse of the matrix L, because this is just the identity. And so what you're doing is operating here, this is what we call the precision matrix sometimes, rather than the inverse covariance matrix. And one of the messages I want to get across is it's actually very convenient to use the precision matrix rather than the covariance matrix. Now, that's the setting. Now, let's suppose we have some measurements of this function phi. Let's suppose that we just measure the value at a point rather than some functional or nonlinear functional. Measurement at a point, simple delta functional of the function. The measurement value is s. There'll be some error. Let's assume it's Gaussian. So the probability density of the function values given the function is just this quadratic. So that's the standard quadratic model, the simplest possible model. And I'm going to use z, it's just a generic normalizing constant. It's always hanging around there. If you say to me, does it integrate to 1? I say, well, it does if you give that the right value. So we don't want to go into the detail. And now the final step in this formulation is that given this likelihood, the density of the function values, given the function, and given this prior here, then I can write down the joint density of the function and the measurements before I make the measurements. This is my prediction of what the measurements will be then using the definition of conditional probability that the density of the measurements given the function times the density of the function is the density of the function given the measurements times the density of the measurements. And this, of course, is known as Bayes' theorem. And it's the basis of this formulation. And of course, it's also, if I just look for the modes, as many people have pointed out, if I'm given a value of s, and I look for the function phi that maximizes this functional probability density, I actually recover a Tikhonov regularized solution to this inverse problem of interpolation. And it's also, in the limit, so let me just say a little bit more before I make that. So what I'm going to do then, if I want to find the mode of my posterior density, I just need to find the function phi that minimizes my energy function centered on phi r, my prior guess, if you like, or the mean of my prior, plus the energy that's in the measurements. Now, in the limit, as sigma goes to 0, i.e. perfect measurements, as often assumed, I recover, I'm not going to prove this, but I recover what's known as dual Kriging in the spatial statistics literature. And dual Kriging, in fact, is the dual of Kriging, by the name, it's an obvious theorem, but dual Kriging is identical with the radial basis function method. And so you get the connection between spatial statistics, Tikhonov regularization, Bayesian statistics, and radial basis functions. And it's absolutely beautiful, I think, that all fits together. And although these results are in the literature in various places, they're not as widely known as they should be, because the reason I stress this, it's very simple, but once you understand this, the generalization to full time-dependent nonlinear problems conceptually is straightforward. The devil is in the details, so you need all the tricks you've got, which is the rest of the talk, really. So in order to get the maximum a posteriori probability estimate, then what I do is I find the function phi, which minimizes this, and of course, because it's a quadratic functional, I can write the thing So equivalently, basically what I want to do is diagonalise the sum of two quadratic forms to get a new quadratic form. H twiddles, phi minus phi twiddles r, where this phi twiddles is the new posterior mean of the density, and there'll be some constant left over, which is the posterior constant, which gives me the new normalisation. And then, because this is a quadratic form going to quadratic form, stupid thing. Quadratic form goes to quadratic form, then I end up with a similar expression that this energy function, when discretized, is a quadratic form involving a new discrete differential operator. And that, in fact, you can show, I won't go the details, but the posterior precision matrix is the old precision matrix. And because I use Tikhonov as my prior, this is actually a sparse, a diagonal matrix. And it has, I should have made the remark earlier, the great advantage of using these Tikhonov type priors is they work on curved manifolds, so you don't have to do any kind of fancy coordinate transformations to get the spatial statistics to work. And that has the very nice and very convenient result that I can update the precision matrix by simply adding a suitable inverse of the measurement variance. So I can update that matrix very easily. Now I'm going to use that as a building block to solve the general inverse problem, the one that Peter was talking about. And I've got my eyes on the target of doing parameter estimation as well. So this is the setting here. So let's suppose I now split my function phi into two parts of parameters and variables. Parameters by definition don't change in time. The variables can change in time, but not necessarily. And the number of parameters might exceed the number of variables. This is often the case in petroleum problems, for example. Now let's suppose, and now this is a special case, but nevertheless it's extremely general, that the variables are driven by a system of ODEs of enormous dimension, 10 to the 6 or more. There might or might not be noise in there with some amplitude epsilon, and let's suppose it's just white noise for the sake of argument. We can make it more complicated, but I don't have much time. Now the standard problem for continuous evolution is given u and v at time 0, you then solve these ODEs in time. If they've got noise in, you have to do some kind of stochastic sampling, but you can find v very easily in principle. Well, in practice, it's fairly straightforward. Now, the next case is where we have some observations. Again, now in general, the observations will be nonlinear functions of the current states of the variables and the parameters. Parameters not changing, and there'll be some observation noise. And the problem is somehow to infer the u's and the v's from this, as we all know. We've talked about that, so that's the general setting. Now, another way of looking at this is to say that the dynamics, so what we're doing is the continuous discrete inverse problem. So we've got continuous evolution and observations at discrete times. There's all sorts of generalizations of this, and I recommend the book by Jasinski, who discusses all these, the references at the end, but that's Jasinski's book, Academic Press, 1970. And you can write down, for the case with noise, the Fokker-Planck equation, where this is the right, and because of my simple choice of noise, I just get a diffusion term, epsilon squared over 2. I get a drift term here involving the dynamics, and because the parameters are not changing, I don't see the parameters appearing here. The parameters are just parameterizing this vector field on the function space. And I can do it in infinite dimensions if I like, but it becomes very difficult for the notation. But some of the theoretical physicists quite often write down infinite dimensional Fokker-Planck equations. I've called it the Liouville Fokker-Planck because I'm particularly interested in the case where there's no noise, which is actually harder when epsilon is 0, particularly for weather and climate models where these functions are actually chaotic and the likelihood functions are extremely complicated. But there's a lovely paper by Jonathan Carter, who's sitting here in the front, on his website, who shows that even in petroleum problems you get chaotic likelihood. So people think petroleum problems are much easier than weather problems, but it's not the case. They're equally difficult, but for different reasons. Now, if I know this, if I could solve this equation, I could propagate my probability density from one measurement to the next. So I make the measurement. So my first problem is my prediction problem. Given a density at time t, what is it at time tn plus 1? So there's no inverse problem there. It's forward propagation of a probability density of an infinite dimensional parabolic equation, which in principle is straightforward, but of course in practice is impossibly difficult. So we need to do some approximations. Now, the next thing then, we make some measurements and we have to find the posterior density. So that's that step there. So what we do is in order to solve everything, we represent the probability density by what we call a Gaussian mixture or a Gaussian sum. So this is the same thing as doing radial basis functions in the function space. And the trick is, and this is the bit that I can't verify at the moment, but because of the success of people like Peter Yan and others in doing particle filters with 20 filters, 20 particles, this is equivalent to a sort of particle filter, except that I'm smearing the delta functions by using these local priors, which are sums of Tikhonovs. And this is how I want to make the connection between particle filters and Tikhonov regularization. And then I choose the weights here, they're all positive and they sum to 1. Now this is great because I can write this thing here. I now have a capital R of these things. R goes from 0 to R minus 1. And my energy function is as before. And that's now a component of this mixture. And it's very important, I think, to choose these matrices here so they're the same for each component of the mixture. Because you've got to store this. And you've got to store all these centers. You don't have to hold them all in memory. So one of the design criteria when working out these algorithms is to try and design them so you don't have to hold each realization or center in memory at the same time as all the others, although you might do for academic type numerical research experiments. But in an operational system, you can't afford to do that. You've got to keep writing them in and out. Now, to sample from a mixture is easy because you just have these weights here. You choose an R according to the probability AR, and then you can sample from this using the Langevin equation. Now this is a Langevin equation in capital N dimensions in the high dimensional space, but it's very easy to do, provided you do a backward Euler discretization. And I think Richard Booth from Schlumberger is going to talk about that on Thursday in a different context, but the same sort of idea. Now, so what we have to do then is to solve this Fokker-Planck equation. So the proposal that I do for doing this is to use the moving point method, or the method of characteristics, which was introduced by Peaceman, Gardner and Peaceman in 1964. And some years ago I showed that you can prove that this algorithm does converge, and it needs some tricks. And I did it in 3 dimensions, so as Gardner did, but it does generalize to n dimensions. So that seems to be a way of doing this, because we need to use an adaptive method in this a grid-free method in such a high dimension. So what we do then is use the method of characteristics. So we use the forward simulator, we call the weather simulator or the oil simulator, and we can move the variables along, the dynamics generate a curve in the function space between one time step and the next. Now along that curve, the probability density then evolves. So if it have a Hamiltonian system, the divergence of this vector field is 0, so the probability density doesn't change along the particle. This is how the particles move without changing their density. Now, I'm not using Monte Carlo because I think this work here, although it was done in low dimensions, shows quite definitively Monte Carlo methods are very inefficient techniques for solving convection diffusion equations of this kind. They're very easy to program, but if you can find other ways of doing it, you can reduce the number of particles even further. And particularly in the case where the divergence of these vector fields is positive or negative, as it is in general when they're not Hamiltonian. So in the general case, you need to change the density according to this, so you know pi along the trajectory, you know this along the trajectory, so you can do a time stepping of it. If you've got a diffusion term, this gets more complicated. Now the great thing about the diffusion, it stops the probability density from going fractal on you and being very hard, and with a bit of luck, although it may not be a Gaussian density, with a bit of luck it'll be monomodal, but this technique will, as Peter Yan and others have shown, the general class of methods can pick up non-Gaussian densities if you've got enough points around. Now we have to actually evaluate this Laplacian in n dimensions, and it turns out, I haven't got time to go through it, but using a Gaussian sum on this, I can actually evaluate the Laplacian as the product of 2 of these precision matrices. So it is actually feasible to do it. Now the thing is, as Peter Yan pointed out, in order to do the propagation, you need to actually aim for where you're going. So this is the crucial step in all this, and I call this the Bayes ruler in my code. So what I'm going to do is at each time step, when I propagate the solution to the Fokker-Planck equation, I'm going to do a preliminary history matching step over one time step and work out where I have to position. So this represents the probability cloud around one of my centres in my density. This represents what it is when it's moved along the trajectory. So I'm going to take the centre at the next time step and go backwards in time to find out where it should have come from so that it lands near the observations, in a manner of speaking. And that means then that my dynamics without the noise, I don't need the noise in it, even if it's there, I don't do that, but this dynamics induces a map from the old time variables to the new ones, and that means then I can take this map G, plug it into the observation operator, and then find the states close to the previous centres, but such that they end up near the observation. So I have to solve this one-step history matching problem. And this is very similar to what Dean Oliver calls the method of randomised maximum likelihood. And Dean's book is a very useful sort, I've already given him one plug, but this is another one, is that you realise it's a very, very difficult problem to solve, but it has been solved, and it's been solved quite clearly. You can do this. So what I'm suggesting is that we do it sequentially. I haven't got results yet that show that this actually does work, but it's conceptually attractive. So this is my, my algorithm, my suggestion of how we can solve high-dimensional problems. And it essentially unifies particle filters, ideas from Tikhonov, ideas from randomized maximum likelihood into one package. And here it goes. So this is what we do. So at time 0, now what I'm going to do is use this notation. So capital S here is all the observations. So S0 is just the observation at time 0, and there's capital SN is the new observation at n, and all the others. This is what people, the measure people call a filtration, because it's a nested set of subsets that keeps growing in time. And that's why this problem, another reason why the problem's hard. Now at time 0, we just do Bayes interpolation and construct a Gaussian mixture that is actually centered on the observations. So we can do that. That's just the same thing as Kriging. So that's one thing what we can do. We know we can do that bit. Now what we do then is at time n, suppose we've got the density at time n, we then history match the old centres to get new centres so that when we propagate them with the Fokker-Planck equation, they end up near the obs. So that's a small adjustment to the prior, so a small change in the prior, but a big change in the performance of the algorithm, because we're looking ahead, but we're not changing the prior. We're not using the observations yet. We're just guiding. It's a form of adaptive approximation. Then we solve the Liouville-Fokker-Planck equation using the moving point method, which means interpolating at the next time step, but it's all fairly straightforward, that. But this is the hard step, doing the history matching. And then when we've done that, we then do Bayes interpolation again, because then we multiply a prior, which is a Gaussian sum, so it's exactly the same problem as doing interpolation, spatial statistics. And then we might, and I haven't done enough experiments to know yet, but I suspect that I still will need to do some kind of resampling or readjustment in case some of the weights get so small, because it may well be that the observations are coming in, the density is getting sharper, and points are becoming unimportant. So like in any numerical method, you need to move things around to put it where you really need it. So I might use the implicit Langevin to do that sampling. So that's what I call the Bayesian smoothing filter, because it's producing a smoothing estimate on the parameters. So in the limit, so I haven't got time to prove, but you can easily write all this down. You can show that the posterior density that you recover for that is exactly the same as you get if you do all the observations in one go. It's actually equivalent. But the idea is by doing it sequentially, you cut down the amount of work. So with a bit of luck, we can do 10 times as many centres. The problem is that you tend to forget what's happening at the beginning. And the history matching step is an attempt to keep a memory of what happens. So that's the basic idea. So just to sort of sum up, so I think the possibility of having a robust general method is very tantalizing. I mean, that would be really nice for us if we could find a general method. Not to say you haven't got to do loads and loads of work each time you do a new application, but it's nice to have a framework where the inverse problems part of the thing is sort of like buttoned up. Now, I think it's only possible if we unify all the different methods. So I try to indicate that. I think we need a bit of everything. So everybody in this big community we need to work more together. So people working on ticking off type stuff, regularization methods, methods that really understand the physics and the mathematics so that you understand in what way your problem is ill-posed to give you good tricks for doing the history matching step. Then you need particle filtering ideas to do the sort of probabilistic side of things. Now, I need to show that this is going to work in practice. I had hoped to get good results, and I'm having a lot of trouble because the software involved, it's a really difficult thing to program this algorithm because it's using all these different ingredients. But I'm gradually getting there, so hopefully next time I give a talk on this, I will have some results, but I've said that over the last 3 months or so. And then I need to start working with some data, so thanks very much. There's the reference to Dean's book.
There's time for 1 or 2 questions.
Oh. I don't know what that means. Okay then.
All right, Dean, get set up.